Hi guys. So I'm going to walk you through the development of the proof of Taylor series. I'm going to deviate significantly from the book in this respect because I think that there's a lot to be gained from a higher level approach than the book takes. And there's going to be a step that I kind of wave my hands at where we interchange sums and integrals, but you should just believe that we have the capability of writing that condition now. So we've already sort of been working with developing Laurent series. Remember that we have this example where we have something like if we have f of z is equal to the sine of z, say over z to the third, that I could think of that as being 1 over z to the third times the series for sine. So it's the sum from n equals 0 to infinity of minus 1 to the n, z to the 2n plus 1 over 2n plus 1 factorial, or if you like, 1 over z to the third times z minus z to the third over 3 factorial plus z to the fifth over 5 factorial, and so on. Everything here is okay as long as z is not equal to 0. Everything converges. And so we can multiply this in, and we get a series that looks like this. So we have a 1 over z squared minus 1 over 3 factorial plus z squared over 5 factorial minus z to the fourth over 7 factorial, and so on. And this thing is called a Laurent series. It's sort of like a series, like a Taylor series, but with this negative exponent piece as well. So this part is like a Taylor series. And this bit over here, this is sort of the singular part of the series. So normally we call this like the singular part. This is often called the analytic part. And so Laurent series basically is a result that says that we can always do this. That if we have a function that has isolated singularities, that we can actually find a Laurent series expansion on any annulus on which the function is analytic. So let's start by defining what an annulus is. So an annulus is a set of the form A is equal to all z's satisfying the property that the modulus of z is strictly between some sort of inner and outer radius. So here r could be negative, sorry, not negative, r could be 0, r could be infinity. This can be 0. This can be infinity. But an annulus generally you should think of as a set that has a hole in the middle of it. So the general picture that we draw for an annulus looks like this. So there's some center z naught. We have this distance maybe is the inner radius little r, and this distance maybe is the outer distance big R, and then the annulus is precisely the piece of that set that's between. So like a ring. So we're going to be interested in the case where functions are analytic on an annulus. So we've been working quite a bit with one really special case of an annulus already, which is the deleted neighborhood. So remember, a deleted neighborhood has the form A is equal to, say, a deleted neighborhood of z naught. Is all points z of the form 0 is less than the modulus of z minus z naught, which is less than, say, some radius r. And those are sets that look like this. It's just a little hole punched out at z naught. So it's a disk that's missing one point in the center, and that's an annulus. Okay, so the reason that we are treating this with annuli is that deleted neighborhoods are how we characterized when functions have isolated singularities. So remember, this is tied up with the idea of an isolated singularity. And so that's going to be a key feature in the theorem that says when Laurent series exist. Okay. So here's the theorem, which is called Laurent's theorem. So Laurent's theorem says that if f is analytic on an annular domain, A R is less than z minus z naught in modulus, which is less than big R, then f has a series representation on the annulus A of the form f of z is equal to the sum from n equals minus infinity to infinity of an z minus z naught to the n. So we're allowing for the possibility now that we have negative powers in the series, where these coefficients an can be calculated with a generalization of the Cauchy integral theorem. So 1 over 2 pi I times the integral around c of f of z divided by z minus z naught to the n plus 1 dz. And that works for all n now, not just the positive n's. And that's where c is a simple closed curve in the annulus that goes around the center z naught. So the setup looks like this. You have an annulus. There's some point in the center z naught. We're saying that we have a simple closed curve inside there that looks like this, that encloses the point z naught. And then with that simple closed contour C, then we can find a series representation for f that possibly has negative coefficients, or sorry, negative powers on the terms of the power series, depending on whether or not f is analytic at the center and all through the annulus, including the hole in the middle, or if it actually has an isolated singularity there. Okay. So how does a proof of that go? So what we're going to do is we're going to use an important idea from geometric series, which recall that if the modulus of z is smaller than the modulus of w, then that means that the modulus of z divided by the modulus of w is less than 1. And in that case, 1 over 1 minus z over w can be turned into an infinite sum z to the n over w to the n. So it's the geometric series formula. That works whenever we have the modulus of z minus w less than 1, so that we're within the radius of convergence of the series. And likewise, if it was the case that the modulus of w was less than the modulus of z, then the modulus of w over z would be less than 1, and it would be the case that 1 over 1 minus w over z is equal to the sum from 0 to infinity of w to the n over z to the n. So these are the geometric series formulas. So this is a trick we used when we were walking through the proof of Taylor's theorem to take the Cauchy integral theorem and get powers of z into the mix. And we're going to do exactly the same move here. Essentially, the proof that we're going to do is going to look like a proof of Taylor's theorem, but twice. Okay. So here's the proof of Laurent's theorem. So the first thing that we're going to do is we're going to assume that the center of the annulus is z is equal to 0 because it makes the computations easier to write down. And the idea of the computations is exactly the same if we put the center at z general z naught or z is equal to 0. So without loss of generality, which means we can do this without changing the proof, let z naught just be the point 0. So we're going to center the annulus at 0. And so this is what our picture looks like. And let's suppose that f is analytic on an annulus centered at z is equal to 0. So we have some outer radius, and we have some inner radius, and right in the middle of that is 0, and we're assuming that f is analytic in the interior of the annulus here. So the first thing that we're going to do is we're going to use the Cauchy integral theorem to, so we're going to pick some z. Pick z in the annulus. Okay, so there's z. Now notice that because z is in the place where that function is analytic, that I can apply the Cauchy integral theorem. Because f is analytic near z, that must mean that f of z is equal to the integral around some little tiny circle, f of w over w minus z dz. So this is the Cauchy integral theorem. So we have this little contour that goes around z that looks like this. This is contour c epsilon. Epsilon here just means it's a small circle around the point z. Okay, now the circle contour theorem says that we can deform that. That's not right. Okay, so what we're going to do is we're going to take that curve and use the circle contour theorem to stretch it out around the whole of the singularity in a special way. And what we're going to get is a contour that looks like this. So we're going to have a circle that goes out here on the outside. So notice this circle is inside the annulus. So f is analytic on this set. I'm going to call this contour C capital R for big radius. But it's inside the annulus. And then we're going to cut in. So we're going this way, and then we're going to go around a small circle, still inside the annulus, but that's inside this circle around z. So note that circle around z is completely contained inside this region. And notice that I've continuously deformed that circle around z to do this. I sort of took it and I stretched it and wrapped it around. So it is not the case that I've pulled the curve through that point at 0 where possibly the function is not defined. I've just taken the green loop and I've sort of stretched it out into the black loop. And I'm going to call this little circle in the middle here CR. And we can call this C in, and we can call this C out. And what the circle contour theorem says is that evaluating f at z is the same as evaluating f, that this integral that I've evaluated around C epsilon can be rewritten as an integral around the outer loop plus the loop, the little path that gets us into the small loop, and then I went backwards around the loop in the middle, so I will put negative CR there because I'm traveling this way so that the inside of the set is to the left. And then I'm going to go back out on C out, and that's going to get me back out to CR. But, as usual, those little straight paths that point in different directions cancel each other, so those don't count. It's not a dz integral, it's a dw. And then that means that this is the integral around CR of f of w minus z dw minus the integral around c little r of f of w minus z dw. So we've reduced the problem into integrals around two circles. The big circle c big R and the little circle that's inside of z called z little r. And the observation that I want to make here is that these integrals act differently because the location of w, our variable of integration, is different depending on which one we're looking at. So let's start by looking at this integral. Where does w live? Well, the w values are trapped inside this big CR, so they're out here. So for that first integral, this is where w lives. And the distance from w to 0 is pretty big, right? So this is the distance absolute value of w. This is the distance absolute value of z. So notice that if we are trapped on CR, so on CR, we have the absolute value of w is bigger than the absolute value of z. But that means that we're going to be able to use the geometric series argument that we said at the beginning, right? If the absolute value of w is bigger than the absolute value of z, then if I could find myself a 1 minus z over w, I could replace it with the sum of zn over wn. So this is going to mean that 1 over 1 minus z over w is equal to the sum from 0 to infinity of z to the n over w to the n. So let's just put a little wall right here for right now, and let's just look at that first integral. Well, what's going to happen? This is going to be equal to the integral over CR. I want to get myself a geometric series so I can get some powers of z in here. So I'm going to create one by pulling a w out, which will leave behind a 1 over 1 minus z over w. And then because the absolute value of z over w was less than 1, I invoke the geometric series argument to get f of w over w times the sum from 0 to infinity of z to the n over w to the n dw. And now I play what I admit is sort of a sketchy game where I'm going to switch the order of the integral and the sum. The reason we can do this is because the geometric series here can be used with the Weierstrass M test to show that this is uniform convergence, which justifies the switch. But the idea is that I'm going to imagine that I've got this integral with this infinite sum inside, and so I'm going to apply the integral to each individual piece. And what I end up with is the sum from n equals 0 to infinity of the integral over CR of f of w over w to the n plus 1 dw. And there's no reason why I needed to keep the zn inside because zn is not integrated with respect to w, so I can pull that out. And that is a Taylor series. These things right here, these are the ANs, the coefficients of the Taylor series. Sum from n equals 0 to infinity of an z to the n. Okay, so we've already seen that when we did the Taylor series argument. This is essentially the same. So let's go back up and see what happens on the other half. Here, the w's are inside c little r. And for w values inside c little r, well, in here, those are closer to 0 than z is. So for these, the distance of w to 0 is actually smaller than the distance of z to 0. And that means that the modulus of w over z is less than 1. So I'm going to use the other geometric series to say that 1 over 1 minus w over z is equal to the sum from n equals 0 to infinity of w to the n over z to the n instead. So this distance now, if this is w for CR, and that distance is the modulus of w, that's smaller than the distance from 0 to z. Okay? But I'm going to play the same game. I need to get some z to the n's somewhere. So Let's do this one in blue. Okay, so I'm going to try to use this formula. So here what I'm going to do is I'm going to write minus the integral over CR. Okay, I'm going to steal a z this time. And I also need to get an extra negative out, because that will leave behind 1 over 1 minus w over z dw. And now I've got two negatives, so those can cancel. And this I'm allowed to use the geometric series formula on. So I get plus the integral over CR of f of w over z times the sum from n equals 0 to infinity of w to the n over z to the n dw. Now once again, you can use the m-test combined with a geometric series setup here to show that this must converge uniformly, and so you're allowed to switch the integral and the sum. That's going to get you the sum from n equals 0 to infinity of the integral on the inside circle of f of w over, okay, well there's n plus 1 z's running around. And I also have this w to the n out here, dw. There's nothing stopping me from taking the z's out like before. So this is the sum from n equals 0 to infinity of the integral of CR f of w. I'm going to rewrite this as w to the minus n dw times z to the minus n plus 1. And that's almost what we want. So what we're going to do is we're going to re-index the series starting from, if I don't want to start from 0, I'm going to start from -1 and then go -1, -2, -3, -4, -5, so I can make the pattern match. And that gets me the sum from -1 to minus infinity of the integral of f of w over now w to the n plus 1. Let's see, does that work? Here I put in a 0 and I get out -1. Here I put in -1. Yeah, okay, so that's the right shift. And you can see that we get the same structure for the coefficients here. So now this is an, but where the an values run from -1 to infinity. And so this is the sum from n equals minus infinity to -1 of an z to the n, where an is equal to the integral over CR of f of w over w to the n plus 1 dw. And over here, an was equal to the integral over c big R of f of w over w to the n plus 1 dw. And what I'd like to do at this point is bring these two halves of this series together. This is going to be my negative term series. This will be my positive term series. But notice this integral is over that inner circle, and this integral is over the outer circle. But the circle contour theorem says it didn't matter how you went around on this circle, that you went all the way around that through the annulus. You could deform one circle into the other, and you're going to keep the same values. So the circle contour theorem says, finally, that this must be equal to the integral over some c of f of w to the n plus 1 dw. And likewise, this can be deformed to the same circle. And that means you can bring both halves together, and you get that f of z is equal to the sum from n equals minus infinity to infinity of an z to the n, where an is equal to the integral over c of f of w over w to the n plus 1 dw. And this object is called the Laurent series. So one thing to notice here is that the particular Laurent series that we get is going to depend on which particular annulus of analyticity that we used. And so we're going to now do some exploration of how we build Laurent series. It should strike you that this is sort of an awkward way of computing them, because I don't really want to have to compute these parametrized integrals around circles every time I want some Taylor series or Laurent series coefficients. And so as we've seen before, usually what we do is we leverage existing Taylor series to generate new Laurent series. So Let me try to clarify before we go on with some examples, kind of what Laurent series are good for. Um, so the first thing is Laurent series track the nature of isolated singularities. What do I mean by that? I mean, if a sum has a finite number of terms that have negative powers, then you have a pole, and the highest power that appears in the negative part tells you the order of the pole. Finite number of negative terms, negative power terms, means Z naught is a pole. Right, that's one thing. Second thing is infinite number means essential. So if you have an infinite number of negative power terms, then you're at an essential singularity. And no terms of negative power means if the function is actually defined at the point z naught, then the function is analytic, and if it's not defined, it's a removable singularity. So either you're analytic at z naught, or you have a removable singularity. Okay. Just like Taylor series, it turns out to be the case that we can use Laurent series to approximate if we're careful. So Laurent series can be used to approximate functions. In a manner similar to Taylor series. And here you could think maybe your partial sums look like sk is equal to the sum from n equals minus k to k of an z minus z naught to the n. You have to be a little bit careful when you're doing these sort of Laurent expansions because you have to go in both directions. You can work with Taylor series or Laurent series when you're integrating and differentiating. Can be worked with in calculus. So, e.g., integration and differentiation. It's a little bit more complicated than it is with Taylor series, but you can still come up with a way to do it term by term, to integrate term by term, and differentiating is the same. And then one of the weirder things that Laurent series do is they give you a way to build Fourier series. If you've not seen Fourier series before, if I have a chance to go into Fourier series before the quarter is over, I'm going to do that. But Laurent series lead to Fourier series, which are maybe the most important series in contemporary mathematics. All right, so remember that a Laurent series is relative to the annulus on which you've defined or found your function to be analytic. So let's look at a function that is analytic on two sort of maximal annuli that don't intersect each other. So the particular function we're going to look at looks like f of z is equal to 4 over z times z minus 4. So if you look at the complex plane, this function has a singularity at 0, and it has a singularity at 4. And so there's actually two natural annular domains that we can consider the function on. The first is the one where we're going to use the annulus that starts at 0, and then the function will turn out to be analytic on an annulus that runs out to the next singularity. So we can think about this as sort of annulus 1. And in this annulus, the trick is going to be to use partial fraction decomposition and then pull the series together. There's another one on the outside of that. So if you actually look at an annulus where we cut the entire disk at 4 out and then look on the outside, the function is also analytic out here. So this is going to be annulus 2. And the function will have a different series on each annular domain because the relationship of the z values to the center of the annulus is going to be different. So let's look at a method that expands the function on each one. So we can start with this one. So if we look at f of z is equal to 4 over z times z minus 4, then we end up with minus 1 over z plus 1 over z minus 4. I'd like to use the power series or the geometric series like usual to find the power series for this thing. Notice this is already the piece of a series that's centered at 0. And so I'm going to expand this about z is equal to 0. So I get minus 1 over z plus, okay, so what do I need to take out here? Minus a fourth times 1 over 1 minus z over 4, which gets me minus 1 over z plus minus 1/4 times the sum from n equals 0 to infinity of z to the n over 4 to the n, which equals minus 1 over z plus minus 1 times z to the n over 4 to the n plus 1. And so there's our Taylor series, or sorry, our Laurent series for the first annulus. We've already seen a bunch of these examples. This is a Laurent series, even though it's not contained in the same sigma notation, because this little chunk that's sitting outside doesn't actually fit the rest of the pattern. And so this is not an unusual presentation to have sort of the analytic part having one kind of structure and the singular part having a different structure. We shouldn't be surprised that the minus 1 over z is only of the power of the powers of the negative terms only go down to minus 1, because it's obvious by looking at f that we're looking at a pole of order 1. The trick to do this on the other annulus is to notice that all of the z values are actually in modulus larger than 4. So the modulus of z is actually bigger than 4 on this annulus. And so that means that I can't use the geometric series like I did over here, because z over 4 would have modulus bigger than 1. So I'm going to flip this over. I'm going to use the fact that 1 is bigger than 4 over the modulus of z. So I'm going to re-express the function on this annulus. This is going to turn out to be an expansion about the center z naught is equal to infinity is one way of thinking about it. So we haven't talked about how we add the point at infinity to the complex plane yet, but the idea is that I sort of flip the disk inside out, and I'm going to think of the center of the series as being at infinity. And the way I'm going to do that is I'm going to plug, I'm going to write f in terms of 4 over z instead of z over 4. So I'm going to write f of z is equal to 1 over z times z minus 4. I would love to be able to use the fact that this is true, but I can't do it unless I do this. So I'm going to take out another z, and I'm going to get 1 minus 4 over z. Now this is a geometric series that can be expanded. So I get 1 over z squared times the sum from n is equal to 0 to infinity of, okay, now what? I'm going to have 4 to the n over z to the n. And that gets me, wait, this is supposed to be a 4 here, sorry. A 4. The sum from n equals 0 to infinity of 4 to the n plus 1 over z to the n plus 2. And this series converges when the modulus of z is bigger than 4. So this is the Laurent series for this function on the outer annulus. And it's useful to have, these are quite different characterizations, but it is useful to have one of these characterizations on each part of the domain where the function is analytic. This is one of the things that Laurent series gets you. I mean, we can't expect that we're going to be able to have a Laurent series that works on that circle if we start at 0 and we go out to radius 4, because the singularity 4 is on that circle. Okay. All right, so that's kind of a basic walkthrough about Laurent series, the existence of Laurent series, working within an annulus, how we use the Cauchy integral theorem to construct two sort of series going in different directions. As we use the circle contour theorem, so implicitly in all of this we're using Cauchy's theorem. And then again, the sort of typical tricks of expansion using the geometric series formula in order to actually compute specific Laurent series. All right, so sorry I'm not in class today. I hope this video is edifying in some way. And yeah, next time we're going to talk about how some more things we can do with Laurent series, and then in particular the way the Laurent series hook up with the residue theorem, and ultimately into more advanced forms of integration. And then also, I would really love to talk about how we can use what we did here to talk about Fourier series. All right, I'll talk to you guys later.